one of the main skills I want you to develop is to determine multiplicative inverses of integers modulo some given modulus. Okay, so we're going to examine how to find the multiplicative inverse of 7 mod 29. Let's do a quick review of the Euclidean algorithm, because that's why we learned it. What's happening now is exactly why we learned it. 29 is going to be 4 times 7 plus 1. Wow, that was quick. I already got to the GCD of 1 right away in one step. And remember what it means. If the GCD is 1, it means I can write 1 as a linear combination of these two given integers. If I just subtract 4 times 7 from both sides of this equation, I'm actually going to get 29 minus 4 times 7 is equal to 1. That's my linear combination that I need. They rewrote it this way up here. So 7 times negative 4 plus 29 times 1 is equal to 1. Remember that we can reduce things piece by piece in an equation like we did in some of the previous examples in this section. So, for example, 29 times 1 is congruent to 0 mod 29, which means we can reduce this equation to 7 times negative 4 is congruent to 1 mod 29. That tells us that negative 4 is the multiplicative inverse of 7 mod 29. But since we're using the convention that integers mod 29 will be from 0 to 28, we have to make a little adjustment. We have to add a convenient multiple of 29, so just add 29 in this case, and we get that the multiplicative inverse of 7 mod 29 is 25. So we said that Z mod n is going to be a field when n is prime. But as you saw in Z mod 6, even though 6 is not prime, there were a couple of cases where you had multiplicative inverses for certain elements. So as long as the number you're taking the multiplicative inverse of and your modulus are relatively prime to each other, you will be able to find a multiplicative inverse. So go ahead and give this hands-on exercise a try. What is the multiplicative inverse of 8 mod 45? Use the Euclidean algorithm. Use this idea of reducing an equation mod 45 and draw the conclusion appropriately. All right. Now let's consider equations. Suppose we have the equation 7x minus 3 equals 5. We want to solve this over Z mod 29. In other words, we're actually trying to solve the congruence 7x minus 3 is congruent to 5 mod 29. That's equivalent to the task that we're being asked to do. All right, well, 7x minus 3 equals 5. We can add 3 to both sides. We get 7x equals 8. I cannot do this. That's not allowed. We can't divide by 7 to get rid of the 7 next to the x. But what we can do, hopefully, is multiply both sides by the multiplicative inverse of 7. So I'm going to write it as times 7 to the negative 1. We're not thinking of 7 to the negative 1 as a fraction. Remember, we're thinking of it as the integer in the mod 29 world, where when we multiply it by 7, we get 1. And look, this is exactly what they say here. So remember we calculated the inverse of 7 mod 29 earlier. It's actually right up here. We got -4 or 25. I'm going to use the -4 to make things easier. It turns out there's a little bit of a typo right here. 7 inverse is not congruent to 7 mod 29. It's congruent to -4. So what we get is x is congruent to 7 inverse, which is -4, times 8 mod 29. That's -32. And again, I want to kick it up. Let me add, let's say we add, which multiple of 29? Well, we can add 29. If we add 29, we get -3. But we're still not in the range we need to be. So we're going to add 29 again. And so we get x is congruent to 26 mod 29. In other words, we solved for x by finding the multiplicative inverse of 7. Okay, so now give this a try yourself. You actually have what you need from what we did earlier in the previous hands-on exercise over here. You can solve this equation over Z45. Okay, so to begin wrapping things up, I don't want you to go around saying that every non-zero element of Z mod any n is going to have a multiplicative inverse, because that's just not true. There's certain criteria for that to happen. I want you to just be able to identify and figure out whether or not there is a multiplicative inverse. So this example is asking you to explain why 3 inverse does not exist in Z mod 24. So think about that for a moment. See if you can come up with an explanation, and then we'll go over it together. Okay, so why does 3 inverse not exist? Well, we can try a proof by contradiction. Let's say it did exist. Let's say we had 3 inverse in Z mod 24. So 3 inverse would be congruent to Z mod 24. Z is that number that when we multiply it by 3, we get 1 in the mod 24 world. What does that mean? It means 3 times Z is congruent to 1 mod 24. So we have 3Z is equal to 24Q plus 1. When we divide 3Z by 24, we get a remainder of 1. Well, what does that mean? If we move stuff around, we get 1 is equal to 3Z minus 24Q. But notice we can factor out a common factor of 3 here. So 1 is equal to 3 times Z minus 8Q. But Z minus 8Q is an integer. You can't have 1 equaling 3 times an integer. It's not possible. Try to think of an integer that makes this equation true. It's impossible. And that's where the contradiction comes from, which tells us that 3 inverse does not exist in Z mod 24. It will exist for other moduli. Moduli is the plural of modulus. Modulus is that number that we're modding by. But it won't exist for 24. to sum up what we've done, modular arithmetic uses the mod operation to reduce. So if ever anyone mentions reduce, hopefully you understand what we mean by reduce. Reduce the answers of all computation to being within 0 through n minus 1. Instead of multiplying, adding, taking powers and all that and getting a big number and then reducing it, it's better to reduce every immediate result. In other words, reduce as you go, which is what you saw us do in a lot of the examples we did today. We can use negative integers. Sometimes negative integers are convenient. And again, if we treat this set 0 through n minus 1 with those specific operations for addition and multiplication we mentioned, we call that set z mod n, the set of integers mod n. In the cases where you have a times some other number a prime congruent to 1 mod n, we refer to a prime as the multiplicative inverse of a, and we write a to the negative first power. Again, that's just a symbol to mean that it's a multiplicative inverse. You won't always get a multiplicative inverse for any element in z mod n, but if you can find one, then we can use it to simulate division. That's how we were able to solve those equations earlier. So go ahead, give the assigned exercises a try, and bring your questions to class.